board before I show you code. So today we're going to do multi-agent programming. So last week we started on Flavius Josephus. So the idea is to compare deterministic data flow with message passing, and then we'll I'll show how to do a design approach, and then I'm going to do a big example, a lift control system. So multi-agent programs are when you have port objects or active objects talking to each other, and it's actually pretty complicated, as you see, when you do in realistic systems. So what I want to do first is compare multi-agent with deterministic data flow. And to do that, last week we introduced the Flavius Josephus problem. This was a historical anecdote. So I explained the story. You can see it on the video, where the soldiers are standing in a circle and they count off every third soldier, and the poor guy has to commit suicide. Okay, so this is a problem in general. If you have n objects in a ring, and if you remove every kth object, so we want to define a program, Josephus NK, which returns the position of the final survivor. So we saw the protocol last time. Last time I showed you a first implementation using active objects, sending messages in a ring. So we have a ring, numbered to n, and they're connected, and there's a message, which I call the kill message, traveling across the ring. And this circulates around and around until there's only one object left. So last time I showed you the active object version. Now I want to start by showing you the deterministic data flow version. And then we compare the two. So I'm going to show it to you first on the board, because I want to do some design, and then I'll show you the code on the system. So each soldier, well, let's call it a victim, has an input stream and an output stream. So let me make sure I get it right. So there's an input stream here and an output stream. So we're not sending the messages using send. The messages arrive on this input stream. So the kill message will arrive as part of the stream, and then the new message will be forwarded on the next stream. Okay? In order to make all of the victims, then we will have a ring of these up to n, and they will be connected using streams. Okay, so there's a stream, the output stream of 1 goes as an input stream of 2. So we have a ring of stream objects. A stream object here is just a list function. Remember deterministic data flow, it's just a list function that reads a list and creates an output list. It's very simple. And it reads the list, and the element on the list is the message. And then it does something, and it creates a new element, and that will be the element on the output. Okay? And that's it. And it will keep running like that. So each of these guys runs in its own thread. And when we start up the system, we introduce the first kill message. Okay? So in order to build this ring, we have to build a ring here. We have to build a ring. Remember, in the active object version, we also have to build a ring. We have to connect them all together. So it's in fact like a pipeline. It's like a pipeline, the ring, where the final one is connected to the first one. So in order to build the ring, let me define a higher order function called pipe, which connects objects together. This will connect objects from 1 to n, and then the input here and the output here will be connected together. And that will make a ring. So that's how we build the ring. So in order to build the pipe, this is a recursive function, pipe. So this is all declarative. Now we're completely in the declarative mindset. So pipe is this declarative function, and we want to build the ring from 1 to n. But in fact, it's going to be done recursively. So pipe is going to call itself recursively. So we have to build a recursive version of pipe. Okay? So the way to do that is to have pipe go not from 1 to n, but from some number L to some number H. Okay? So we have L plus 1 up to H. And then we can make a recursive definition. So this part will be the recursive call, and this will be the full pipe. So with this we can define the pipe. And then we have, of course, the input stream, and we have a function f that we use to create these guys. And then when you call pipe, it will return the output stream. So we define this pipe function, and once we have the pipe function, we can build the whole thing. Okay? So maybe I can show code now. Okay. So I'm going to make a file which has all the code. So the first part, so there's going to be some definition. So I'm going to skip over that. Let me show you the code for the deterministic data flow version. So this font is a little bit too big, or I don't know, maybe it's okay, I guess, we'll see. So we see here, this is like a utility function, pipe, and it will create a pipeline. So the idea is that it goes from L to H, so the victims are numbered, 1, 2, 3 up to N, so from low to H. So if L greater than H, then we're done, then there's no pipe. Otherwise, I create a victim, so the function f will actually create the victim with an input stream, and the name of the victim is L, and it returns the output stream, and then we make the recursive call to pipe with L plus 1. So this pipe will actually create the whole pipeline. Okay, so this is a utility that we need. And now the actual protocol. So this is actually the full program. So here is the function Josephus 3 and k. Here is the victim function. This is the one that actually reads an input stream and creates the output stream. So it will have the name of the victim, my name, which is I, and then XS, the input stream, and it returns an output. So this is just a list function. So it will read case XS of kill XS. Remember the protocol, there's a kill message, okay? So let's see, how does it work exactly? So S is the number of surviving nodes that are alive, and X is the position. Each time we make a step, we count X. So if S is equal to 1, then that means this one is the last survivor. And last is a global variable, which is then bound to the last survivor, and it returns nil. When a stream function returns nil, then the stream is empty. Okay. Otherwise, if S is not equal to 1, then I have two possibilities. X mod k is 0, that means poor guy has to commit suicide. So I do kill X plus 1, S minus 1, and then XR. So what is this doing? This is the output stream. So there's the kill message on the output stream, and then this function disappears. So there's no recursive call. So I'm just passing the input stream to the output. So the victim disappears. But if x mod k is different from 0, you see there's actually a recursive call here. And that means the victim keeps surviving. Now it will keep going with xr. So this victim will keep going until x mod k is 0, and then it disappears. Okay? And finally, if the input stream is nil, then the output stream is nil and everything terminates. So this is very clean. Okay? When the victim dies, the poor victim dies, it disappears from the ring automatically because there's no recursive call. And when the whole ring, eventually the whole ring will disappear. So when we find the last survivor, then the output is nil. This output goes to all the other ones that are there, if there's any left, and they will all disappear. Okay? So this function implements the protocol, the Flavius protocol. And then we have here in the body the initialization. So here we call the pipe for building the pipeline. It goes from 1 to n. And here we have the function that creates the victim. Notice it's an anonymous function. It actually creates a thread where the victim call is inside the thread. So this is actually a stream object. Thread victim ISI. IS is the input stream. And this whole thing returns the output stream. And I is the number of the victim. So these two arguments are the same as the arguments here. And then there's a trick. We need to connect the output of this pipe to the input. So this argument is the input, and this argument is the output. So this one, the output is ZS. But if we make the input equal to the output, then there's no messages. And the thing doesn't do anything. So we have to put the initial message. So the first input is kill 1n, followed by ZS. So this actually puts in an initial message. Okay, here. And it connects the rings with an initial message. So this thing will actually run. Okay? And will give me the Josephus. So you see the code is very dense. It's very dense. It's only a few lines. So let me run this. Okay, here I have some examples. So here you can see I do Josephus 5.2. Remember we did last time, which shows me 3. That's good because that's the same result we got last time. Now the problem with poor Flavius, lucky Flavius, he was in position 28. So 43, he was in the position 28. And of course you can do much bigger ones. So if you have 1,000 soldiers and you count off every 100th one, the survivor will be number 876. So this is a very concurrent program. This Josephus with 1,100 will actually create 1,000 threads in a ring, sending messages very fast, and they will basically disappear. So all the ones where x1k is 0, the victim will disappear. If it's x1k is not 0, it will not disappear yet. But it takes a long time, because it has to go through 100 victims before it actually makes one disappear. Okay? So it's going through a huge number of stream messages to do this. So here we have a program with 1,000 threads, a concurrent system. So this is doing pretty nicely. So now let me go back to the active object version. So here's the active object version. So this is the actual victim class. So here, every message is explicit. Each of these methods is actually a message. Kill excess, and we have to do a send. So if it's alive, and if s is different from 1, if x mod step is equal to 0, then alive is false, and then I send a successor message. So this corresponds to the kill bar xr in the active object version. This one is actually kill. So in the active object version, it's going to be like this, And here it's going to be, here we have a recursive call because it's not dead. So there's no alive bit Boolean in the deterministic data flow because the object just disappears when it's dead. It just disappears. So here, every single message you have to send it explicitly, okay? And then you have to initialize things. So this corresponds to the pipe. This is all corresponding to the pipe routine. First I create n objects. These are new active objects, so I have this new active primitive. I connect them in a ring, so AI is the successor of a.i is a.i plus 1, and then I have to also make sure that a.n is connected to a.1, and then I put the initial message in here. So you see the two programs are doing the same protocol, but the code is very different, It's interesting, In fact, let me run this one. Let me first define the active object. Because this is the primitive. Okay. And then this one. So this should give exactly the same result as before, if we're doing things reasonably. 3, that's good. 28. And 876. This one is actually slower, a lot slower than the deterministic data flow. And the reason why it's slower is because the dead objects are not removed. They stay in the ring. So this ring stays the same. So here I have this alive bit here. And if the object is dead, I just forward the message. You see, I get kill XS. If the object is dead, I forward. So the dead objects are kind of like zombies. They get a message and they forward. That's all they do. But they're still in the ring. So they take time, because each one is in its thread. So this version is actually slower, less efficient than the deterministic data flow version because of that. Now, in fact, we can optimize this version. That's what I want to do now. We can actually update the ring. We can remove the dead objects from the ring. And then this version will have about the same speed as the deterministic data flow, because the number of messages will be the same. See, here the number of messages is actually a lot bigger, because dead objects will keep working until the end. So if I have 1,000 objects, even if there's only 5 living survivors and there's 1,000 soldiers, then to remove each one of those 5, I have to go through 1,000 forwardings. All these forwardings, okay, to count. And then I'm counting to 100. So 100 times I have to count, 1,000 times, and each time I go around one whole loop, I'm counting one, a live one, okay? So it's really very slow to keep the dead ones in the ring. So we can optimize this by removing the dead ones. So notice the deterministic data flow already does that optimization. Huh? It's very easy in the deterministic data flow to do that optimization. But here, this protocol is not doing that optimization. So I'm going to modify this code so that I change the ring, okay? So let me make a picture. I think I have a little bit of room here to make a picture. So the idea is the following. If I have, so the ring is, let me say the ring is like this, huh? And this one dies. Okay, well, what I want to do is I want to update the ring so that the successor pointer will point to the next object. Okay, you see that, huh? So I will remove, so this object stays, but this successor pointer from the previous object, I wanted to remove, to skip the dead object. You see, so I want to update the ring. But it's not that simple, because in order to update this successor pointer, I'm here when the object dies, huh? This is the object that's dying. I need to know the predecessor. In order to update this guy's pointer, this object needs to know its predecessor. That means I also need predecessor pointers. Okay, in order to do this, I actually need predecessor pointers. You see why you cannot do it if you don't have predecessor pointers, huh? Because this node cannot access the previous one. So you need predecessor pointers, and then you have to also update the predecessor pointer. So when this object dies, this predecessor pointer also has to skip that one. So basically you need to have links going two directions, okay? And then this guy will send a message to its predecessor to update the successor, and it will send a message to its successor to update the predecessor. Because modifying the ring is done through messages, of course, huh? The only way to modify the ring is to send messages. This is a multi-agent system, huh? So basically, in order to remove this dead object from the ring, I need to extend the data structure. I need predecessor pointers. Then I have to update both of those. Okay? So let me show you the code for that, the optimized version. Okay, let me make the font a little bit smaller. Let's see, how do I make it? Let me make this 212. Now you can see the code. So the code is a little bit more complicated now. So if you notice, now I have not just successor attribute, but also predecessor. I have one extra method. I have set successor and set predecessor. And here, if x mod k is 0, alive is false, and now I will update the ring. I will send to the predecessor, I will update its successor, I will set successor, and to the successor I will do a set predecessor. Okay, you see that? And then I will do a kill message. So I have these two extra messages now that I add. So that what I do is I have to send 3 messages now. Huh? I send a message to the predecessor to update its successor pointer. Okay? And then I send a message to the successor to update the predecessor pointer. Actually, this is a predecessor pointer, and this is a successor pointer. So I have to send a set successor message to my predecessor, and I have to send a set predecessor message to my successor. Okay, you see how it works, huh? And then this object is removed, and I have a new ring with one less object. Okay? You see how it works, huh? Now, but we still have a little problem now, because we have 3 messages in the system. This is concurrent system, huh? I do this send, poof, the message goes in there. This message. So I have now 3 messages concurrently. This this send will not wait. It sends the message and then it continues immediately. So it's concurrent. So at this point here, I have 3 messages alive traveling in the system. And now, is it still correct? What if the kill message, what if I don't do correctly the updates? In fact, the kill message, it should only see a correct ring, not a partially correct ring. What if the predecessor pointer is correctly updated, but not the successor pointer? What if I have a partially fixed ring? Here I have 2 messages, and in order to do the kill, I have to do both of these messages before the kill arrives there. The kill has to always see a correct ring, a ring with correct successor and predecessor pointers. So actually we have to prove that now. We have to do some reasoning here, because this is not necessarily correct. You see the problem? If you do first the set successor, and then the kill arrives, then I have a half fixed ring. One of the pointers is good and the other one is bad, so that the dead node is half in the ring. So that's kind of weird, and don't know really what happens there. So we have to make sure that the kill message will only, when it arrives at an object, that object will be part of a correct ring. We have to prove that now. Okay? It's not just adding messages and everything's fine. You have to think, because this is a completely concurrent system. In fact, what if I do the kill first and then these 2 after? Then it'll be incorrect. It turns out this is correct. But why is it correct? You see that it's not so simple, that it's not so obvious why this is correct. You understand that, that there's something you have to think a little bit here. And in fact, we can prove this is correct because of a property of the active objects called the FIFO message property. That means if I send 2 messages, I send and then I send another one, the first one I send will arrive first. The order of the messages will never be switched. That's actually a strong property, and that works because we have streams which are extended step by step, which are like lists. They are ordered. So our active objects have this FIFO property. Notice that the internet does not have that. Internet protocol does not have FIFO. If I send 2 packets on the internet, they can arrive in the opposite order. There's no guarantee of the order. But here there is a guarantee because of the streams. That means if I send a successor message and it arrives, so this one, successor will go to a single node. It will go to the predecessor, and this one. Whereas the kill message will go all the way around. It goes all the way around the ring before it comes back here. The kill message will go all the way around and will eventually come back on the other side. But these 2, the set successor and set predecessor, will immediately arrive where they have to be. Okay? So we can actually prove that these 2 messages will arrive before the kill message arrives at their nodes. Okay? The set successor, because we did the send first. We do a send of a set successor to here, and then we do a send of a kill later. But because of FIFO, this set successor will arrive first at that node. And it means it will fix the successor pointer before the kill message arrives. And the kill message is even slower because it has to go all the way around. So that's okay, that will not break anything, because it will just make it even slower. So the set successor arrives first. And the same for the set predecessor. So the set predecessor, which sent to the successor, will arrive before the kill message. You see that? So that is important. If we didn't have that, this would not work. Okay? It would be broken. And if you put the kill, so the order here is very important. Huh? If we put the kill message here, for example, the send of the kill here, then it's incorrect, this program. Huh? The kill message must encounter a correct ring with one less victim in there. Okay? So because of FIFO and because of this order, it works. You see that? You see that there's some reasoning here. Huh? If the sender was using IP, like on internet, this would not be correct. Okay? Well, but if it's using TCP, which has an ordered byte stream, then it's correct. So one of the things about TCP is that it adds ordering. And it has to work for that. Huh? If you remember your networking course, or you have this windowing, you have these sequence numbers. So TCP has to work to get the order. Huh? So that's important to have an order. Okay? So what I'm saying is that this is the fix, but it looks very simple, but in order to make sure it's correct, you have to think a little bit. Huh? You see that? You see why, yeah? Okay. So I can run this now. So this is supposed to work, okay? The initialization is also a little bit longer because it has to initialize both pointers, the successor and the predecessor. So I create the objects, I connect them into a ring with the successors and the predecessors. So I have to do both, and then I send the kill message. Huh? I have to connect both directions. Huh? And then it should work. Oof, seems to work. And this one it's faster now. Huh? You can tell it's faster. Huh? If you look at, see the previous one, is this one. So look at it now. Eventually the 876 arrives, but this one is faster now. And if the arguments are larger, the difference is even bigger. Okay? So this is the active object version. I call this one the short circuit version because it removes these nodes, so it makes that short circuit between the two, the successor and the predecessor. And it has to do some work for this. So you can see that the active object protocol is kind of lower level than the deterministic data flow. You have to do some, in French, chipotage, you have to do some tricky stuff to make sure it works in the right way. And you have to think a little bit. You have to really worry about every single message. And you can see the code is kind of long here. Huh? There's lots of stuff here in the initialization. So it's actually, I don't know exactly how much is the difference, but it's like more than twice as much code. Okay. So that's one of the differences between the deterministic data flow. So here, let me go back to the deterministic data flow. So this one is very compact. So we have this little pipe and we have this initialization, but the actual protocol is just this thing. It's very compact. So deterministic data flow has the advantage of being very compact when you can use it. Okay? But you cannot always use it, that's the problem. It only works if your program is deterministic, whereas active objects will always, even if it's non-deterministic. So a language like Erlang is always doing the active object version. Huh? It doesn't have this thing. But this is very useful for when you have deterministic computations. So this protocol is deterministic, Flavius Josephus, because you're always determining, it's always the same survivor, there's no choices. It's a deterministic protocol, so it's perfectly fine. You can write it in deterministic data flow. Okay? Okay, so let me make there's some slides actually. Let me explain a little bit. So this was the protocol, okay? So let me just give some summary of the comparison of active objects and deterministic data flow, both implementing the same protocol. So in the active object, each solder is an active object, which is basically a passive object inside a thread, which means that all the messages are serialized. If you remember, an active object has a thread, okay, and it serializes all the messages so that internally it's always sequential, one after the other, okay? And here on the deterministic data flow side, each soldier is a stream object, so it's just a list function. It's a function that reads a list and returns a list in a thread. So those are the two ways of soldiers. Here in the left we have a class. In the class, like in Java, whatever, with slightly different syntax, but this is how you would do it. So in a language with active objects, you would do something like a class, and you have a kill method, and the method implements the Josephus protocol. But here, on the other side, you don't have a class, you have a function that reads a stream and outputs a new stream. And it has a case statement. So you notice that the methods here kind of correspond to the case statement here. And both of them have to build a ring. So you have an initialization with successor and predecessor. But here you just build a ring of stream object connecting the streams together. Okay? And then we did this short circuit protocol. So let me explain that. So in order to go fast, so the active object implementation, we can optimize it to remove the dead victims from the ring, because otherwise you have to traverse them all the time. The idea is you have to update the successor pointer of the predecessor and the predecessor pointer of the successor. And it's a little bit subtle, because you have to do the modifications before the kill message sees the new objects. So this crucially depends on the FIFO property of the send of active objects. Okay, so I assume that you understand that, that you can explain that. Why is it crucially dependent on the FIFO? Okay, but then that's fine. In the deterministic data flow implementation, it already does the short circuit. It's automatic. It's actually an interesting thing, because the short circuit is done by the recursive call. Either you do a recursive call, and this is when the victim stays alive, so you call it again because it's alive, or you don't do the recursive call because it's dead. So you automatically remove it. You don't call it, okay? So not doing the recursive call means the victim no longer exists. Okay? So that gives you a comparison. And in fact, if you look at the size of the code, this one always is going to have shorter code. It's more compact than this one. But the problem is you can't always do this one. That's the defect. Otherwise, I would say only do this. But you cannot do it if you really need non-determinism, like in the client server. Okay? Then you need active objects. But you can see that if you do more of this, the code will be shorter and it will be automatically very efficient. So this is a very efficient paradigm. It's automatically doing very nice optimizations. Okay? Okay, so that gives a comparison. So that's important. We see these two different paradigms, and it's important for you, even if they're very different, in your head to see how they can compare them. It's like oil and water, but they they look very different, but in fact you can compare them, okay? Okay, so let's go on now. Let's go on to more bigger multi-agent. So what I want to do now is do a really big, real multi-agent design, much more complicated than Flavius Josephus. And that's actually not so easy. So first, I want to explain to you a methodology, an approach. So this is very concurrent, and the messages are going anytime. Any object can send a message at any time to any other object. So this is a massively concurrent program, huh? So whenever you have that, you should be scared, huh? Because they're hard. They're hard, okay? Concurrent programs are hard. So the only way to do it is to be very methodical, to use a very systematic way. Otherwise, if you start hacking one of these guys, it's over, huh? You never get something that really works, okay? You can test it, seems to work, and then 2 days later it doesn't work. No, it doesn't. It's not good, huh? And in early days, that's what happened, huh? In early days, what I'm saying is that in the 1980s or 90s, huge amount of bugs happened because of that, huh? So there are famous bugs, infamous bugs, like radiation therapy machines, which I mentioned. This is one of the most famous ones, where if you type fast, you have a concurrency bug, and the routine that reads the keyboard is running on the same processor as the one that controls the radiation, okay? It's the same processor. So concurrency bug, and the radiation dose is 1,000 times higher, okay? So people died from this, okay? So this is important, huh? So I'm going to show you first a methodology, and then we're going to show a big example of a pretty realistic one with lots of agents. So in the real world, you're going to see lots of these, huh? So we're going to program with these agents. So they're like active objects. A collection of agents, each one has internal state, and they send messages to each other, okay? Now notice deterministic data flow is actually already doing that, but in a restricted form. Do you remember the digital logic simulations we did? The full adders and the latches and so on and so on. That's already multi-agent, but they're deterministic. So deterministic data flow is kind of like a simple form of multi-agent. But now we're going to do the full thing. So with port objects or active objects, we go beyond deterministic data flow, and our programs can actually have non-deterministic behavior, and you need that in the real world. You need non-determinism because you may have timing constraints that depend on the real world, or other kinds of ordering. Things that happen in the real world are not always deterministic, and the program has to accept whatever order the real world imposes. Remember the client server? Whichever client messages arrive first, you have to treat it. So you need non-determinism to interact with the real world. So this is important. So what I want to show you now is the basic principle, how you make such a program, okay? It has to behave correctly for all possible interleavings of the agents. So all the agents are executed concurrently, and they can send messages anytime they want, anytime they feel like it, okay? And still the whole thing has to be correct, and it can be non-deterministic. So you can see it's not a simple problem, huh? Okay, so first I want to explain a little a methodology with some basic ideas, and then after that I'll show you a big example, okay? So a concurrent component, or an agent, okay, it's a procedure with inputs and outputs. When I call that component, I create an instance, which is the agent. So the concurrent component is like a class, and an agent is like an object, huh? So you can have many agents that have the same behavior internally. So we will use port objects. In Flavius Josephus we use active objects. they're almost the same thing. An active object uses a class, whereas a port object just has a case statement, okay? So remember the digital logic example, we had this full adder procedure with 5 arguments, okay? These are actually streams, these arguments, input streams and 2 output streams, and whenever you call full adder, you create a new agent, okay? A new instance, a new agent. And when you create agents, there's different operations. So there's actually 4 basic operations. So you know some of them already. Yeah? Instantiation is when you create a new instance. That's reasonable. It's like a new instance of a class. Composition is when an agent is built with other agents inside. Okay. Linking is when agents are connected together. And there's different ways of connecting them. And then restriction is when an agent internally, it has things that you don't see on the outside. So let me show you an example of this. So this is an old example. This is the full adder. So this is the full adder procedure. So this one is written in deterministic data flow, but it's still a multi-agent program. So we have AND gates, OR gates, exclusive OR gates. Each of these letters is actually a stream, each of the identifiers. So whenever you call the procedure, you will create a new full adder with 7 new gates. So whenever I call AND G, I will create an AND gate. Okay? Each one of these has a thread in it. So the full adder has 7 threads. Okay? And then there's linking. Linking means, for example, the output stream of this AND gate, which is C, is going to be the input of the other one. It's agents that are connected to each other. And there's something called restrictions. So the A, B, C, D, E are streams that are internal. You don't see them. So you can build agents out of other agents, kind of compositionally, yeah? Okay? And then, so the composition, the restriction, instantiation, okay? So these are all the concepts that you can see. So you see them already here, okay? And agents are connecting to each other. The agents are connecting, and because it's concurrent, we have to be very careful how the agents are connecting to each other, okay? So we've seen already connections where you can only send one value. That's sometimes important. It's like acknowledgement. And that makes it very simple. We just have to wait for one value. It's purely deterministic. So these are called one-shot links because you can only have one value. So these are the data flow variables, and you use them for acknowledgements, typically, okay? If you want to read many things, you have streams, okay? And this is one source. That means there's only one sender. So you have an agent sending messages to another one, like a pipeline. So these are deterministic. You have one sender, and it's deterministic. So this is important because we have this very non-deterministic system. So if a part of it is deterministic, it's good to know that, okay? We won't want to make everything non-deterministic. Because otherwise we also have many sources, the many senders. This is like a client server where you have many guys sending to the same agent. So in the language we have called this a port. Remember the port? So anybody can send a message to a port. So this is non-deterministic. Okay? So languages like Erlang are based on this. Okay? So these one-source links are deterministic, but the many-source links are the ones where many processes can send messages. Okay? So this is the methodology. So after the break, we're going to do the real thing. But I want you first to see in your mind the kind of thing we're doing. So how does it work? Well, it starts by informal specification. So you write down what you want. And we'll see. a lift, we have elevators, lifts in a hotel, you press buttons. So we have this. Then we define different kinds of components. Lifts, floors, the controllers, lift shafts. And then you have message protocols. So it's not just randomly sending messages to these agents. There's actually protocols. Remember we saw message protocols like RMI and callback and asynchronous. So between these agents there's message protocols. And then each agent has a state diagram. So that's the internals, the brain of each agent. So this is actually the hardest piece, okay? The state diagram is the hardest one, and we're going to spend a lot of time on this. Once you have this, the rest is easy. Writing the code is very easy once you have the state diagram. So all of the work is basically here. So you have to do it like this, because otherwise you can't just say every object consents to anybody. Yeah? And once you have the actual code, you can test it, but that's not enough. You have to reason about the code, like we reasoned about the short circuit protocol. You have to think and do some reasoning to make sure that things are happening right. Okay, because it's very concurrent. Huh? So we're going to do state transition diagrams. So let me just very quickly show you what it looks like. So here's an example of a transition diagram. So I go back now, so you see what it looks like. So there's these states are the memories of the agents. So each agent has an internal memory, and that's the state. So all of this is inside the brain of the agent, okay? And it might be in a certain state, and then it receives a message, and then we have this notation with a slash. It receives a message, and it transitions to another state, but it maybe also sends a message, okay? So it's in a state, it receives a message, and it maybe sends a message, and it goes to another state, okay? So every agent, you have to make sure that in every state it can receive all the possible messages. So this is what's called a finite state automaton, okay? So normally the number of states is finite, but it could be infinite, huh? There might be a huge amount of information, and so we will have examples where it's infinite, huh? Of course, you can have huge data structures inside the agents, okay? So this is how we're going to define it when we define it. So this gives you the basic idea. But so far, we have not done anything yet, okay? So now let me introduce the actual system we're going to design, which is a lift control system in a hotel. Okay? So this is a lift control. So this is, in the good old days, when I traveled before COVID, I went to conferences. They usually in these big hotels with huge number of elevators, 25 floors. They maybe have 6 elevator shafts. So, and going up and down all the time, people pressing buttons. So this is the kind of system we're going to design. A lift control system with lifts or elevators going up and down. They stop at floors and people pressing buttons to go to the floors. And it's completely concurrent. People are pressing buttons arbitrarily and the thing has to work. Okay? So this is actually similar to the actual control systems in hotels and apartment buildings. And it's a typical kind of big multi-agent system that you see in real life. So I'm going to start by doing some kind of informal specification, basically explaining what it has to do. And we identify what are the components and what are the message protocols. And then the real hard work is here. We have to design the state diagrams. So in the system we are designing, there's actually 3 components that are different. The controller, which is controlling the lift up and down. The floor, which is where the lift stops, so the floor is also an agent. And the lift itself, which knows which floors it has to go to. Okay? And buttons can be pressed arbitrarily. So you can press a button when you arrive, when you walk up to a floor. You can also press buttons when you're inside a lift. Okay? and arbitrarily, and it has to work. And then I'll show you the code for this. And then there's two things we have to do. Test it, of course. You always have to test, huh? A program that is not tested, does not work. You know that, huh? I think you have enough already experience. But you also have to verify, which means you need to do some reasoning. You have to understand why, at some conceptual level, why it's working. So we'll do that too. So it's not enough to test, because testing can miss weird cases, okay? But verification, if you reason, you can cover the whole thing, okay? So you need to do both of those. So let me show you first the system, the basic system. So we have lift shafts. So there's 3 here. This is a hotel with 3 lifts. We have lifts. So each of the boxes is an agent. We have floors. So there's n floors here. So each floor is also an agent. We have users, which are the humans. We're not going to implement the inside of the human, but the human can send messages, press buttons. So it's part of the system, because messages can come from one of these guys, users. And then we have the controllers, which are controlling the motor, which are basically the motors. So each lift shaft has a motor, which is either in the basement or up on the roof, which controls how the lift moves. Okay? So there's 4 different kinds of components here. The users, the floors, the controllers, and the lifts. So we're going to build this system, and I'll show you the code for this. And so we're only going to design controller, floor, and lift. I'm not going to design the users, okay? The users are assumed to exist, but they can send messages, okay? So maybe let's just do one more slide before the break. So there's message protocols. So the protocols are actually not so complicated in this case. They're not so complicated. You could do more complicated ones. So for example, a user can send a call message to a floor. So floor F. When a user is in a lift, it can send a call F message to a lift, which means I'm in the lift and I want to go to floor 10. I press the 10 button. Okay. The floor can actually ask for a lift to come. So it sends a call F message to the lift. The lift sends an arrive when it arrives. And then this acknowledgement is when the lift is allowed to leave. So this is a one-shot thing. It's just an acknowledgement. So when I bind the act, then the lift is allowed to leave again. And the lift also talks to the controller. We're assuming the controller is doing step by step, one floor at a time. Okay, for simplicity. So the lift wants to go to a floor D, and the controller moves the lift and tells me now I'm at floor F. Okay, so the lift and the controller will be talking to each other. The floor and the lift will be talking to each other, and the users can press buttons whenever they want. Okay, so this is a summary of the message protocols in this system. Okay, and then we're going to do the state diagrams. But now I do a break, and after the break we will build the system and I'll show you the code. So we're going to build it, and so you know the protocol, you see the protocols, and you know in your mind how it works, huh? Users press buttons, floors talk to lifts. So lifts will go to floors. Okay, so, and because either the floor will call the lift, if I'm at a floor and I press the button, I want the lift, or I'm inside the lift, the user is in the lift and wants to go to a floor. So the lift knows what floor it has to go to, because the floor is either the floor calling the lift, because there's a user pressing that, or a user inside the lift has pressed the button. So floors will go to lifts. But let me start with the simplest state diagram, just to get you into the way of thinking, so which is the controller. So the controller is basically, it moves the motor up and down. So it has 2 states. It's either stopped, the lift is stopped, or the lift, it's running, so the lift is moving, okay, up or down. Okay? And So we're going to model this. So in real life, of course, it's going to turn on and off a motor. But here we model that it takes time by using a timer. So we have this timer agent, which I call TID here, which is the timer agent. You can send a start timer message, and it gives you a time, 5,000 milliseconds, and it gives you the identity of where it sends the reply back. And then 5,000 milliseconds later, it sends a stop timer message, okay? So in our program, we're going to do, it's a simulation, huh? So it's not real hardware. You can actually make it real hardware, but to make a simulation, we're going to use this timer because things take time. So the controller will move the lift up or down. So we're assuming that moving one floor is going to take 5,000 milliseconds, okay? Why is so slow? Well, because when we simulate it, we're going to see the simulation running, huh? So you can put whatever time you want there in the simulation, but we're going to show you the simulation. So the idea is that when the floor moves, when the lift moves, you send a timer message to the timer, and the timer sends a stop timer reply back. So here's the state diagram. So the controller is initially stopped, and the state of the controller is this thing. It's a stopped or running. It also knows the floor, F, so this is a constant, F, and it knows the lift it's attributed to. So each controller is like a lift shaft. It knows what floor it's stopped at, and it knows what lift it is controlling, okay? So this F might change, but the LID will never change, okay? So what happens? The lift, when it wants to move, it says, I want to go to floor destination, okay? So the lift sends a step message saying, step destination. So if the lift is at floor 5 and it wants to go to floor 10, it sends step 10 to the controller, okay? Now there's two possibilities. The controller is already at floor F. It knows the lift is at floor F. So if F is equal to dest, then you do nothing. Then the controller does nothing. And you go back to the same state. So this is a state transition, huh? So this slash here, the left is the message you receive, and the right of the slash is the action that you do, huh? So if you receive a step message and dest is equal to F, then you do nothing and you stay in the same state. Okay, that's reasonable. Now, if you receive a step message and F is not equal to dest, here, then you do something. Now, we're going to make a simplified controller. It only moves one floor at a time, tuck, 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 because maybe the lift has to stop at the next floor, so it's not going to do many floors. It's going to go one floor at a time, very simple. So we're going to send a start timer message to the timer, and we're going to have a new F. So this F and this F is not the same. There's a new F. So if F is less than dest, then it's F plus 1. That means I'm moving up. Otherwise, I'm moving down, it's F minus 1. So new F, here, whenever I say new something, it's the new state. Okay? So new F will either be F plus 1, so the old F plus 1, or the old F minus 1. I either go up or down one floor. So then I go to the running state and make a transition, and I stay there until I receive a stop timer message. So that's going to come 5 seconds later. So when I get the stop timer message, I go back to the stopped state, and then I know I'm at the floor. So I send an at F message to the lift. Okay, to LID, that's a send of a message. So this is kind of the notation, Message to somebody is a message I send, okay? And on the left side of the slash, I receive messages, okay? But I can receive from anywhere, but when I send a message, I have to send to somebody, okay? So this is how the controller works. When the lift wants to go to floor, it sends a step message to the controller, and the controller does something, and then it sends an at message back to the lift, saying you are now at floor F. So, for example, the lift is at floor 5, and it wants to go to floor 10. So it sends a step 10, and eventually it gets an at 6. Okay, and then it sends step 10 again, and then it gets at 7, and so on, until eventually it gets an at 10. So the controller will do floor by floor, okay? Because it's important, because maybe you need to stop at a floor. Okay, so this is the controller's state diagram. So you see how it works, huh? For example, here, these messages with booleans, it's kind of like an if statement, huh? If f is equal to dest, I do this. If f is different from dest, I do that. And you see the timer here, start timer to the timer. I receive stop timer. And then I send an at message back to the lift. See how it works, huh? So basically this is doing the protocol, huh? If you look back here, it's doing the protocol between the lift and the controller, huh? The lift does a step, controller does stuff, and it sends at message back, huh? So what we show here is the controller's state diagram. So this is a simple state diagram. It's basically doing two things, huh? It's moving the lift, which we simulate with a timer here, because we're actually doing simulation here, huh? And it's also checking which floor I'm at and moving in the right direction depending on the floor. So it has this comparison between F and dest, okay? Between the floor I am now and the destination, the ultimate destination, okay? So this is the simple controller state diagram. Okay, is that reasonable? You understand the notation? So this example I give it so that you can understand the kind of notation, and I explain how it's done. But now let's go to another one, and I'm going to design it with you. So I'm going to write on the board, and with a blank slide, so it gives white. So now we're going to define the floor. That's okay? That's readable? I hope it's readable like that. So now I'm going to design the floor with you so you can see how I think. Okay? We're going to build the floor state diagram incrementally, piece by piece, so you can see how you think when you build it. So how does a floor work? So the floor is in several different states. So this is a floor that I'm designing here. So the floor can be idle. So most of the day, the floor is just sitting there and doing nothing. So this is the floor object. So it has a state. Let me call it not called. That means I have not called the lift. What the floor can do is it can call a lift. Okay, now let's say I walk up to the floor, so this is readable. I walk up to the floor and I call the lift, I press the button. So we're assuming there's only one button, not an up and down button. You can do up and down buttons, but then you have two messages here instead of one. Yes?
Can we switch to a slide that is less white? Because we can't see the...
You want the slide that's less white? Okay, maybe I do black.
Okay.
Maybe I do a black thing. I don't know, this is an experiment for me, because it's hard for me to turn off the... It's good? Yes. Thank you. See, that's the kind of feedback I want. Okay, good. So we do like this. So the next best thing to turning it off is to display a black slide. Okay. So I'm not called here. Now I press the call button, and then I go to another state. So I call this one called, and the idea is that I have now called a lift. Okay? I'm in the called state. So usually when you press a button, the light goes on, it's calling a lift. But I have to do something. I have to actually call a lift. So the idea is I send a call F message to, let's just say a random lift ID. Okay, and of course the floor knows its floor number, which is a constant. So it will send a call F message to some random lift. This is what happens when I do call. Okay, okay, that's good, huh? And then what happens is eventually the lift arrives, and then the floor goes into another state, which I call doors open, because it has to open the doors. Arrive, and then there's the act which is allowing me to leave, huh? And then there's more stuff. So eventually there's an arrive here, okay? And then the doors open. And again we're doing a simulation, so we're assuming the doors are open for a certain time. So we're going to use the timer again here, huh? So I'm going to do start timer. Let's say 5 seconds again. Floor to the timer. So we're assuming we have these timers, okay? And then eventually there's going to be a stop timer message arriving. Okay? And now the lift is allowed to leave. When the doors close, so this is I'm modeling now the opening and the closing of the doors, huh? So the lift is allowed to leave, and that's the acknowledgement. So I bind it to some constant unit. So the ACK is an acknowledgement to the lift that it's allowed to leave. So this is a one-shot thing, huh? So this is very easy. It's just a one-shot, and it's allowed to leave. So this is the basic cycle of a floor, okay? So the lift leaves, and I'm back again at not called, okay? But I'm not done yet. Now you have something very interesting. So this is the basic normal cycle of a floor. But this state diagram is by far not complete. The problem is that every state can receive every message, in the worst case. So when I'm here, I can also get a call message. Fine. I mean, the guy is pressing call and he's very impatient. Okay, well then I'm already called and I get a call message. What do? Well, I have to handle it. So I have to have another state transition here. If I get a call message here, when it's already called, what do? Well, I do nothing. So this is an easy case, huh? I don't do anything. Okay, so fine. But more things can happen, okay? More things can happen. For example, the doors are open, and I also can call the lift when the doors are open. Stupid, but people can do it. Huh? So I can also get a call message here. Okay, so I have to add these extra states. If I don't add them, the system is buggy. Because these call messages, okay, they have to be treated. Okay, if they're not treated, they will stay in the system and they will be arriving at other times. Okay, but now it's still not done yet. Assume now I'm in a hotel with many lift shafts. So I have been in hotels where you have 6 lift shafts. That's not so many. That's not unusual. Okay, and they can all arrive at the same floor. That means when I'm here, when the doors are open, another lift could arrive at the same time. So I can have another arrive message. Another arrive message. And let me just say A here to make it not ACTA. So another lift can arrive. So in the real case, each lift has to have its own timer. Huh? Each lift, when it arrives, the doors open. It has its own timer. But let me make a simplification here, because that just makes the code complicated. Let me just say that when the lift arrives, that all the doors close at the same time. So let me just say that A is equal to ACK. So these two acknowledgements, I make them equal. That means when I do ACK is equal to unit, A will also be equal to unit. Huh? That means when the multiple lifts arrive, then they will all close the doors at the same time. So that's kind of weird simplification, but I just want to make the code simple. Normally you would have to have a separate timer for each one. Huh? You can do that as an exercise. Okay? But you can still have more stuff. There's a big thing missing still in this. So can you imagine there's something still missing here. A big thing in this diagram. It's still not complete actually. Something important can happen that is not in the diagram. Can you see what? Can you imagine? A lift can arrive at a floor even if nobody at the floor presses the button, okay? It's because somebody inside the lift pressed the button for that floor. Huh? That means when the floor is at not called, a lift could arrive. Okay, you can have this. I can have an arrive. It just randomly arrives at the floor. Nobody called. It's because somebody in the lift wants to go to that floor. Okay? So it can also arrive here. So this is exactly the same as this kind of arrival. Huh? I have to start the timer now. Okay? As before, the lift arrives normally to... So I start the timer, and then when the timer stops, the lift can leave. So there's two ways the lift can arrive. Right? It's because somebody in the lift has pressed the button for F, or it's because somebody at the floor has called it. Okay? So am I done now? Is this a complete state diagram, nothing missing? So the trick is, every state has to handle every message. Is that true here? So what are the possible messages here? The messages are call and arrive. Okay? A floor can be called, or a lift can arrive at a floor. Does each one of these states handle both call and arrive? What do you think? Is anything missing now, or is everything there? You tell me. So that's the thing, yeah? Every state has to handle every message, even if it does nothing, huh? Like this. Because if you do not treat that message, the message will stay in the system, and it will be handled later by somebody who does accept the message. But that's not what we want here. We want to handle all the messages right away. Okay? You see that? So here, in not called, I have call and I have arrive. Doors open, I have call and I have arrive. Called, I have call and I have arrive. So it seems to be good, huh? I'm handling all possible messages in all possible states. See that? So that's reasonable, huh? So this is implementing the floors protocol. Okay? Okay, so that's nice, huh? There's a more complicated protocol, which is the actual lift itself. The lift is by far the most complicated. This is still very simple, okay? So I leave the complicated one for last, which is the lift. So let me do the lift. So once you have this diagram, it's very easy to write the code. Huh? The hard part is writing this diagram. Huh? Writing the code is very easy. And in fact, there are tools that let you draw the diagrams and they will generate automatically the code. Huh? The problem is the actual diagram. Okay, now let's do the actual lift. So the lift is harder. And the reason why the lift is hard is because the lift can go to multiple floors. What happens if I have a hotel with 25 floors and I press 5, 10, 15, 17? Well, then the lift has to go to 4 floors. So we assume now that this is a pretty smart lift that remembers all those floors, because sometimes you have very stupid lifts when it only remembers 1 floor. But if you have a hotel with 25 floors, that's really, really a pain. Because if somebody presses floor 25, and you're on the bottom, and you're going up, and you want to stop at floor 5, sorry, no luck. You have to go all the way up to 25 and back down. So that, most of the real hotels, they are smarter than that, okay? Because people don't accept that. Okay, so the lift actually remembers a sequence. Okay? Okay, so let me say the state of the lift. So there's a moving bit, which is false here. There's a schedule, which I assume initially is nil. I'll explain what it means. And there is a position, so this is actually the floor. Okay? So the lift has a data structure called a schedule. Schedule is actually the list of floors it has to go to. Okay? It's a list of floors. Okay? And assume the lift is sitting there, it's not doing anything. And then I press a button to go to a floor. And then I will go to a floor. Or I will start moving actually, yeah? I do call N. Okay? And N is not the same as where I am now. Okay? Then I have a new schedule, which is equal to a list of one element, N, and I send a step message to the controller. So this, remember, the guy is going to talk to the controller, huh? It's also going to talk to the floor. So now I'm here. I'm still at the same position because I only change position when the controller sends me an at message. Huh? I have a schedule here. And here it's different from nil. And here the moving will be equal to true. So as long as the schedule is different from nil, that means the lift has work to do. So I will summarize that in this moving thing. You don't strictly need it because you can always look at the schedule, huh? But it's nice to have a boolean that tells you that the lift is moving. Okay? Well, what if it's here and somebody does another call? Huh? Oof. What if I have another call? So the lift already knows it has to go to floor N, it's at pause. So maybe it's at floor 5, it has to go to floor 25. And in the lift, someone says, I want to go to floor 7. Okay, well I have to define a new schedule. So which is, what is it? It could be, there's many possibilities, huh? It could be append, schedule, N, or M, sorry. So I put M at the end. This is kind of stupid, huh? You see, you can have a smart scheduler, huh? If I'm at floor 5, and I have to go to floor 25, and someone says 7, putting the 7 at the end after the 25 is actually not so smart. Huh? You actually should have a smart one. So you can actually have a function called, how do you say? There's different functions. You can define it. Smart schedule, which takes the position, the schedule, and M, and returns the new schedule in a smart way. So while the lift is going up, of course it can stop, huh? So, but this is correct. Appending it at the end is correct. It's just kind of dumb, but it will work, okay? And then, so remember I have sent a step message here to the controller, which means I will get an at message eventually from the controller with a new position. Okay? And there's two possibilities. Either the new position is where I want to be. So I'm going to use, the notation is similar to Oz notation. Schedule.1, the first element. Or it's going to be, different from schedule.1, or it's at and here it's nPos is equal to schedule.1. Okay, this is, I still have to do the other stuff. So it's actually a loop here. I send step to the controller, I get an at here. If it's not the same as schedule.1, then I'm not done. I have to do another step actually, yeah? I can do this. Step schedule.1 to CID. Okay, and the new position is equal to nPos, because I have changed position a little bit though. So this is one possibility. So this is a loop, this is kind of like a while loop. I do step here, I get the at from the controller, but if I'm not where I want to be, I send another step to the controller, and I continue. So this thing loops until eventually it comes out of the loop here, where nPos is equal to the scheduler, and then I have to send a message to the floor. Arrive at to schedule.1. So this is actually sending an arrive to the floor. Okay? You see that? So, and here this is, let me call this one wait for doors. So the lift is now arrived here. The floor will open the doors. Eventually close the doors. Okay. So it actually closed the doors. So there's different ways it can close the door. So the closed door is the ACK. Wait, ACK is a closed door. Okay. But then there's two possibilities. Maybe I'm completely done, or maybe not. If schedule.2 is different from nil, then I'm not done yet. I have other floors. But if schedule.2 is equal to nil, so wait ACK and schedule.2 is equal to nil, okay, then, so I still haven't written down what I did here. So there's another loop here. When I'm done waiting for the doors, I get the ACK, and if schedule.2 is different from nil, that means I have more floors to go to. So I have to go back to do that. Whereas if schedule.2 is equal to nil, I'm done. But I have to set the new position here. New position and the new schedule. So the new schedule is equal to schedule.2. The new position is nPos. So now I have a new schedule, which is schedule.2, which is different from nil. Okay. But I'm not done yet. I have to send a step message to the controller. Schedule.2.1 to CID. Okay. Ooh. I have to do all that, and that gets me going to the next floor. See, so I wait until the doors close. If schedule.2 is not nil, the new position is my new position, but the new schedule is schedule.2, and I again ask the controller, but I go to the next one, which is schedule.2.1. And I go back here, and then again I will do the same loop here, and eventually I will arrive at the floor. So I have actually two nested loops here. I have a loop where I'm going step by step one floor to get to the floor, next floor I'm going to, and then I have to look at the schedule to see if there's even more floors. So I actually have two nested loops here. So this, if I maybe do something colored, I can do a colored thing. So this at and this at, this is a loop, whereas this wait and this wait is another loop. So this is like an inner loop, and this is like an outer loop. Okay, so you can see these state diagrams. It's like a programming language. You can do funny things that are like loops, and some of the tools let you write it like loops, okay? And they will automatically compile it down into state diagrams, okay? Here npos is, sorry, the new position is npos, and the new schedule is nil here. So when I go here, it means I'm back, I'm done with everything. So you see there's a lot of stuff going on here. Huh? Okay, let me go to the code now. Okay, let me go beyond this black slide and to a lit up slide. So this is the lift. This is a nice picture of the lift diagram. So I do a call here. The new schedule is n. Each time I do another call, I will add n to the schedule. So that can happen completely concurrently. Yeah? That can happen at any time, even while the rest is running. Huh? Now, here I have done a step, and here I get an at. If I'm not at the right floor, I do another step. So this is a loop, and eventually I exit the loop here when the position is equal to schedule 1. And then I wait for the doors, and then there's two possibilities. Either schedule.2 is different from nil, then I have more floors to do, or schedule.2 is equal nil, and then I'm done, and I go back to here, and the lift is idle again. Okay? So this is actually two nested loops, but they can be interspersed with calls happening at any time. Okay? See how it works, huh? And now, and we still have some things to complete here. So if I'm here, I'm at floor pos position, and I do a call, but n is equal to pos, then I don't have to move. I can just open the doors immediately and close the doors again. Okay? Okay, and now there's a subtlety. When I'm here, actually I do not treat the call message here. So what does that mean? When I'm here, I do not treat any messages. I only wait for the acknowledgement. So this, you have to be very careful for this, because it means you could have deadlock. If this thing never happens, then the system will block here. But this is, the floor is going to give me this. I know that. I can show that by reasoning. So because I only want to treat the call messages here, because otherwise it's too complicated. So if I type, I press the call button and I'm here, it will not be treated here, but the message does not go away. It will be treated when I'm back here. And I guarantee, because this wait will eventually be true, I guarantee that I will do it, okay? So you see, you have to be a little bit subtle, the reasoning, okay? Same here, Here there's no, you cannot do a call message when the lift is waiting for the doors to close. But that's not a problem, because you know for sure that this wait is temporary, so that you will eventually always go back to this state, and then you can, or this state, and then you can handle the call message again. Okay? So notice you have to always update the schedule. The problem with this is that what makes it complicated is this schedule. The schedule, which is the list of floors that you have to stop at. So that's why the lift is a little bit more complicated than the others. It has this schedule thing. And this is actually, you can actually have smart algorithms for the scheduler. This algorithm is actually known. It's used for disks, for rotating disks and a disk head. You know, when a disk head is like an elevator, you have in a circular disk, you have the blocks, and it's going out to the edge and then back. It's like an elevator going up and down. So you don't want the disk head to go like this. You want to go all the way out and then all the way back. So a real elevator is the same. If I type many floors, I want to go all the way up to floor 25, and then all the way down, and I do all the intermediate stops. So the schedule function should be smart enough to insert the n in the right place. Okay? So this is how it works. And now we can actually write the code. That's actually the easy part. So we have these three diagrams. So the controller, okay, the black slide, the floor, and the lift. So we have these three state diagrams, and we can convert this into code very easily. So let me show you how that works. So let me show you by starting with controller. So here's controller. The way, it's always the same, in fact. So the controller, this is the controller function. When I run this, I will create a new controller with controller ID, which is what I can send it, the identification. Notice there's a timer. So I have actually a timer object, which I've also defined, which you can see in the code, which is very simple. It reads, it gets start timer, it does a delay, and it does a stand stop timer. So each controller has its own timer. Okay? And then the code is this code. Notice it has two nested case. So it's always like that. The code is always two nested cases. Okay? You have the case of the state and the case of the messages. So the state can be running or stopped. Here I'm using a syntactic sugar of Oz, where if I have a record, a state that's a record, I can actually put it in the argument, okay? So I get motor, F, and LID. So the motor can be either running or stopped. And in each of those two cases, I have an internal case. So this is exactly following the state diagram. Huh? So motor and running, stopped, are the two states, okay? And inside of each, I handle all the messages. So in the running, I can only receive stop timer. In the stopped case, I can receive a step message, okay? And then I have different possibilities, according to the state diagram. See, so this is exactly following the state diagram. So let me go very quickly back to the state diagram. If I can find it here, PowerPoint. So that, the code I show you is exactly this, This is, you can translate this to two nested case. The case for the states, and then for each case you have a message, okay? Okay, and now we can look at the other one. So here's the floor. They're a little bit longer. Sorry, it's hard to put them all in one slide. Again, so this is the floor. Each floor has its own timer. You have not called or doors open. And in each of these cases you have the arrive and the call message. Arrive and call, okay? And it returns to the state. So this is just a translation of the state diagram. You just automatic. And there exist tools to do this. But in this course, I'm showing you the thing, the real thing, And then the final one is the lift, which is a little bit more complicated. I've added some browsers here so that we can see the thing running, in the simulation. So you have call here, message. So here, it's interesting. I've flipped the two cases around. You can actually, the two cases, you can do them in any order you want. You can do first the state, and then the message for each state, or you can do the messages, and for each message you can do all the states. It's just a convenience. So here I have the state on the messages, so the call message, and then depending on what is going on, I do things. And then I have the at, so this is from the controller. and I do things. So this is all following the state diagram. Huh? So all of this can be run. And then I have this function called, this procedure called building, which makes a building with Fn floors and Ln lifts. So I create, for each lift shaft, I create one controller and one lift. And then for each floor, I create the floor, okay? So this creates a whole builds the whole building, okay? So I can run this now. After all this, you have to see the code running, right? So let me create a building with 10 floors and 2 lifts. So send to f.9, call. So it's moving up. Okay. 8, 9, open doors. Close doors, and we're done. But you can do many things, huh? You can have 5, okay, and you want to go to lift 1, so I have to do this, for example. So I have to go to 5, and also 4 and 1. So it's doing it all concurrently. Floor 4, floor 5. Okay, it's already floor 1. So it goes to all those places. So that's the simulation, and you can run it. So I'll put the code on the Moodle one. So yeah, so when all the state diagrams are defined, we write the code. So we have 3 components, floor, lift, and controller. Okay. And now we have to do testing and verification. So testing is you invent weird scenarios where people are pressing buttons in weird ways, but that's not good enough. You also have to reason. Okay, and if you find a problem, you have to go back to an earlier stage in the methodology. You have to fix the problem. Maybe you fix the state diagram. Maybe you change the message protocol. Okay, or even maybe your informal specification is wrong. You have to change it. So here's an example of some verifications. So you can actually prove properties of this code. You can prove the lift will always eventually stop at a floor that is part of the lift schedule. So if you look at the state diagram, you can prove by sequencing the loops that no matter what messages arrive, that if a floor is in the lift schedule, that the lift will stop there. It cannot avoid that floor forever. So maybe I want to go to floor 25, huh? I can slow it down by pressing all the buttons below. This is what practical jokers, they sometimes do in hotel. Huh? They come in there, they see a little lady pressing 25, and they go, tick, 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 tick. And so the lift will go very slowly because it stops on every floor, but it still goes up to floor 25, and you can prove that. Huh? You can also prove that if you send a call F to a lift, then the lift will eventually arrive at floor F. So you can prove it combining using the first one. Huh? If call F is sent to a lift, you can prove that the schedule will eventually contain F, and then you can prove it using the first property. So using these, you can prove that it actually will work correct in all the possible cases. Okay? Okay, so let me now just make a conclusion. So this is a really nice example showing where you need all 3 pillars. So this you have seen, I'm sure, I hope, in some other courses. There's 3 pillars of software development: design, test, and verify. So we have here a nice design methodology. You build a state diagram and you make sure that every state handles all messages, okay? So this helps to ensure the sound system. Then you test it, including weird things called corner cases. And then you verify, you prove properties. And there's actually software tools to do this. So there's a tool called a model checker, which you may have seen in a course by Charles Pêcheur. No? Have you seen that? Or you will see. So you could actually prove properties of the system with software tools which exhaustively examine the whole space So these are called model checkers, okay? So this can let you do verification. So with that, you can be sort of sure that it will work until it doesn't. Okay, so let me conclude. So we have added ports, non-deterministic many-to-one. We can write multi-agent programs where we have many agents that are concurrent, sending messages. The behavior is defined by a state transition function. You can write it as a class, okay? We have compared active objects and deterministic data flow with this Flavius Josephus problem. You can see how the two paradigms are very different, but they can do similar things. And I show you how to build these big systems. So many real-world systems are like this. In fact, sequential programs are kind of exceptional. Most real-world systems will be a little bit multi-agent. Okay, that's it. So let me stop there. So I hope you like it. Experiment. I put the code on the Moodle, so you should experiment with the lift control system. Let it run. Change the timer. You can actually do many cases very fast. Remove the browsers, make the timers very small. You can actually do very much testing with this. Okay.